So we will start. I kindly ask all participants to deactivate the microphone. Otherwise, I will be obliged to deactivate, of course, except Professor McDonald, who is our invited speaker, and deactivate your videos to allow to better take profit of the lecture. So we start.
Very good.
Calling for understanding. Good morning to you, Professor Arthur McDonald. Good afternoon to all participants, and good morning. And bonjour à vous, bon après-midi à vous, buon pomeriggio a tutti voi. Guten Tag, buenas tardes a ustedes, buenos días a ustedes. Welcome to Paris and to the International School of Astrophysics, Daniel Chalonge-deVega, for this 11th session in this year within the Nobel program I organized this year, and it's a great pleasure, a great honor to welcome here today Professor Dr. Arthur Bruce McDonald from Queen's University and Kingston, Ontario, Canada, Nobel Prize in Physics 2015. Gordon and Patricia Gray Chair in Particle Astrophysics in the Department of Physics, Engineering and Astronomy and Queen's University, where is now emeritus from 2013. And the director experiment of SNU, the Sunbury Neutrino Observatory, and the lecture, precisely the lecture of today, and the subject is particle astrophysics in underground laboratories. He got the Nobel Prize in Physics precisely for the discovery of neutrino oscillations, or so-called neutrino transformations, which demonstrated that neutrinos have a mass, and doing that, this was and it is the solution of the old so-called solar neutrino problem. And independently, Takaaki Kashita in Japan with Super Kamiokande confirmed or discovered also the transformations of neutrinos amongst the three types with atmospheric neutrinos. This have a fundamental, extremely impact, not only for the physics of neutrinos, but for the standard model of particle physics in general, because came a call for an extension, and for the known old problems in astrophysics and open new ones for the evolution of the universe. I should say that neutrinos at the heart are known particles at the heart of modern astrophysics and for the understanding of the universe and for fundamental physics. Just briefly, I would like to say that Professor McDonald was born in Sydney, Nova Scotia in Canada, grew and was educated in there in the Dalhousie, I don't know if I pronounce, or Dalhousie place and schools and bachelors and masters there in 1964. And in, where he said in one of his biographies that was an inspiring place and inspiring his own choice for physics. In 1969, he got the PhD in California in the Institute of Technology, and then after in Charter River was working from 82, from 69 to 82, and then leave for Princeton to got a professor position there till 1989. Left Princeton to join the Queen's University and Kingston, where he is there till today, always active, because it's no lab and the experiment is active. And I should say that also, I mean, very briefly, that have received many important and prestigious awards, which will not be the last. And the said Benjamin Franklin Medal, of course, the Nobel Prize, as I already mentioned, the fundamental physics breakthroughs, the same year he got the Nobel Prize, and also for, I mean, all the team of the collaboration of the SNO. Many, I mean, fellow of the Royal Society and the Royal Society Academy in Canada, many prizes and prestigious prizes and recognitions in Canada and worldwide. Was visiting professor and visiting scientists in CERN, of course, and in Oxford, in University of Hawaii, and many others places. And last but not least, has said from his own work, an humanitarian involvement and work in the from last year, in which the time of pandemic, which we all know, from Italy, I mean, one of the members of leading members of different dark matter particle experiments for detections, being in Milano and staying confined there, then have this initiative to apply this technology of the detectors for to construct mechanical ventilators at low cost and in high number production. And Professor McDonald became involved very and leading in the different collaboration, in particular in Canada, became leading this other collaboration, and very welcome. And with that, I should say that, which became also a patent in CERN, the mechanical ventilator Milano, said is known like that. And with that, I thanks again and give you, the floor is yours, Arthur, please.
Thank you very much. It's a pleasure to be with you here today, and I think everything I'm going to say to you today is done in large-scale collaborations, and as Professor Sanchez mentioned, we were very fortunate in the last year, 2020, to have a group of people from the dark side collaboration that are pursuing dark matter particles pivot their research to develop a new form of ventilator, which is low cost, it's open source in terms of having published directly the design that we came up with. And under a contract with the Canadian government, we have, through several manufacturers, provided over 7,000 of these ventilators in the Canadian stockpile of ventilators. And because that stockpile is large enough now, the discussions are underway for donation of such ventilators to countries in need, which I'm sure you all know are very substantial around the world. So it's a nice example of how people who normally do basic science have the capability to make other contributions. And so I'm going to talk today about those other let's say, the day jobs of such people. And this will be a fairly broad-ranging presentation. I'm told that these lectures sometimes attract people who are not familiar in detail with the field that we're talking about. And they're also Nobel lectures. I will start with how the Sudbury Neutrino Observatory made an impact in the field of particle astrophysics. I'll talk about how underground laboratories are a very important part of this field and of accomplishing these things we are attempting to measure. And I'll use as an example a couple where I have been involved in working, particularly SNOLAB in Canada and the Gran Sasso Laboratory in Italy, really with measurements that are made of particles which penetrate through the rock above these laboratories. In the case of Sudbury, that's about 2 kilometers of rock, where we really shield out cosmic rays that otherwise would interfere with our detectors. We're able to make measurements that really span the full range of our universe, in the sense that we study neutrinos, in the case of Sudbury Neutrino Observatory, neutrinos from the sun. We study neutrinos from the Earth, in fact. We also study dark matter that has an influence in how our Milky Way galaxy takes this shape. And of course, dark matter has major implications on the whole formation of structure in the universe. And so really it's covering a wide range of distance scales, as you can see, just as labeled on this particular slide. But it also addresses quite fundamental questions. By getting away from cosmic rays, which in Canada make beautiful displays of, or things like them make beautiful displays of things we call the northern lights, where they make the atmosphere glow. Our detectors, which are also looking for light, very often do not glow because of this intervening rock. We can study how the stars like our sun burn and create the elements from which we're made. We can study the basic laws of physics for even the smallest fundamental particles. In this case, I'm talking about neutrinos, which are whose basic properties we have been able to add to in terms of our understanding. And we also can study the composition of our universe and how it has evolved to the present time by studying these neutrinos, by looking for particles we refer to as dark matter that have apparently substantial gravitational effects in our universe, but do not fit into our current knowledge of ordinary matter. And by being underground, we not only can observe things that come through the rock, but also make very sensitive measurements of rare forms of radioactivity, things that have lifetimes on the order of 10 to the 25 or 26 years. So you have to accumulate a large amount of these materials and look for the occasional decay. And in this case, rare forms such as double beta decay that does not emit neutrinos in the process can tell us about the properties of those neutrinos that are fundamental, both in terms of placing them within our theories and also from a universe and the cosmology of how the universe has evolved. Neutrinos, many of you, of course, are very familiar with them, but some of you may not be. Along with electrons and quarks, they're so far, we always as scientists say, so far, we haven't been able to find any way to subdivide them further. They are the basic building blocks. Neutrinos come in 3 flavors. They're described as a part of the standard model of elementary particles, which has been extremely successful in all other measurements to date. They only feel the weak force. They don't feel the electromagnetic force or the strong force. And so if they're passing through matter, they basically only stop if they hadn't hit the nucleus of an atom or the electron surrounding that nucleus head on. And so they can pass through 1 million billion kilometers of lead with only about a 50% chance of stopping. And so they penetrate easily through the rock above us, but that makes them very difficult to detect. And so their properties have been the least known among the basic particles. The original standard model said that they should not change from one of the 3 flavors to another, or oscillate, which was a process that was suggested might occur. But if they are observed to oscillate or change their flavor, the implication of that is that they have a mass greater than 0. And up to this point in the standard model, they had been postulated to have a 0 or at least extremely tiny mass. The standard model goes back to the level of quarks, leptons like electrons and neutrinos, and the force carriers that represent the electromagnetic interaction, the strong interaction, and the weak interaction, in that that's the way in which these interactions transmit forces between particles. Protons and neutrons, which are in the center of an atom, contain various combinations of quarks. Electrons surround those protons and neutrons that are made from up and down quarks in the ordinary matter from which we are made. But there are also higher mass versions of all of these particles that are observed in high energy events at accelerators or in cosmic rays, for example. As I said, the neutrinos only feel the weak force, and of course, all of these particles with mass feel gravity. The neutrinos are produced in enormous numbers in the radioactive processes that power the sun, the nuclear fusion that powers the sun. Each of these particles has a matching particle which is made of antimatter. And if a particle and its antiparticle find each other, such as a positron finding an electron, they annihilate each other, providing pure energy. In the case of positrons, producing a burst of gamma rays that's very effective in positron emission tomography. So the standard model provides a basis for the electromagnetic weak and strong forces, but has not yet included gravity. And in fact, there are many theories that are attempting to include gravity as a further way of unifying all of the forces and understanding how they influence our universe and its development from the very beginning. The Higgs boson, which you have heard of, I'm sure, in publicity from its observation at CERN, provides the mass mechanism for all of the particles except, it appears, the neutrinos, because we have in fact observed that neutrinos do change their flavor and therefore have a finite mass, and it's a different mechanism than the standard mechanism for the other particles. In addition, there appear to be particles that I'll talk about later called dark matter particles that don't fit anywhere in this scheme of things. And so they may give us a clue as to what's happening beyond the standard model, in addition to having substantial influence on how our universe has evolved. Going now to the sun and the solar interior that we're able to study by looking at neutrinos that are produced there, in a number of experiments over the years, starting with very basic experiments using chlorine, 600 tons of cleaning fluid containing chlorine. Ray Davis and his collaborators observed neutrinos with a threshold here compared to the number of neutrinos being, well, reaching the Earth that come from the various nuclear reactions that power the sun. In 1968, right away, as he made his measurements, Ray Davis, working at the Homestake mine, began to see results which are fewer than what is calculated here by Jean Ecole and later others like Sylvain Turchez, who contributed substantially to an understanding of our sun and to the neutrino production in the sun. The experiments I'm going to talk about, I will talk about predominantly, is the SNOW experiment, Sudbury Neutrino Observer experiment, which had a threshold here and which was sensitive essentially primarily, if not exclusively, because the HEP reaction is so small, to boron-8 neutrinos. And similarly, through different mechanisms, the Super Kamiokande experiment was also sensitive to the same neutrinos produced in the sun. Now, all of these different processes that are circled have been observed directly, and this model for how the sun burns is known to be very valid. But in 1984, when the SNOW collaboration first came together, the situation was that there were too few electron flavor neutrinos, electron flavor neutrinos being the only kind that can be produced in the sun, compared to the solar model calculations by Bacall and others. So either those calculations were incomplete or incorrect, or perhaps the electron neutrinos created in the sun were changing to another flavor and eluding the past experiments that were sensitive only to electron neutrinos. Herb Chen, who was a professor at the University of California at Irvine, in 1984 proposed that if one could obtain 1,000 tons of heavy water, then one could measure separately using deuterium, in a way I'll show you in a moment, the electron neutrinos in one reaction and the sum of all three neutrino types in another one. He and George Ewan were the original spokespersons for the 16 of us who came together in 1984 to start this collaboration. And the reason why deuterium, or heavy water as it was contained in, the reason it is useful in this way is that there are several reactions. First of all, one where specifically an electron neutrino hits the deuterium, in particular the neutron inside the deuterium, changes it to a proton and a fast-moving electron that produces Cherenkov light in the heavy water itself. There's a second reaction that is sensitive equally to all neutrino types. This is referred to as a charge current reaction, and this is a neutral current reaction, where the signature is a free neutron in the heavy water, which of course has a very low neutron absorption coefficient. But when it does absorb neutrons, it produces 6 million electron volt gamma rays that can be used to detect the presence of that neutron. And in fact, we had 3 different ways to detect them and measure this reaction. Comparing these 2 reactions enables you to tell whether the electron neutrinos detected exclusively in this first reaction are equal to the total number of neutrinos, and therefore there is no change of flavor, or whether, as is the possibility, as observed by Davis, that only 1/3 of them survive because of neutrino oscillations. And that, in fact, is what we observed when we made the measurements. You have to be very careful when you do these experiments, because any gamma ray which has an energy high enough to split apart the deuteron, producing a free neutron, which means any gamma ray greater than about 2.1 million electron volts, can mimic what you would be observing from neutrinos from the sun, producing the second reaction. That meant that the heavy water we were using, of which we had 1,000 tons, had to be purified to the point that there was less than 1 radioactive decay per ton of water for the principal radioactivity from the uranium and thorium chains. We were able to build this in a very deep mine, I think it's the deepest in North America, 2 kilometers deep, 7 Eiffel Towers deep for a Paris reference, and to build an enormous detector, really 10 stories high, containing 1,000 tons of heavy water, which amazingly we were able to borrow from the Canadian government stockpiles for $1 for over 10 years of use. It's normally used in the CANDU style nuclear reactor that also uses natural uranium. That heavy water, highly purified, is contained in an acrylic sphere 12 meters in diameter, 5 centimeters thick, surrounded by almost 10,000 8-inch or 20 centimeter diameter photomultiplier tubes in a cavity filled with ordinary water, but highly purified, in a 34 meter high and 22 meter diameter cavity, which at the time was the largest cavity at that depth ever excavated, sealed with a material that makes it impermeable to water, but also impermeable to the radon that normally comes from the rock containing uranium, trace amounts of uranium. Same thing that gives you a problem with radon in your basement, and this was almost the biggest basement that you can imagine. This is what it looked like during construction. We were very careful. We maintained ultra clean conditions, class 2000, of all the air in the cavity as we were constructing it. Every worker took a shower and wore clean lint-free clothing like you would do in manufacturing semiconductor chips. And we were able to produce this detector with less than a gram of dust distributed on all the inner surfaces. And we were able, therefore, to reduce the radioactivity and measure it to be substantially lower than the signal we were getting from the neutrinos from the sun. That required a large amount of technology. Here you can see my colleague David Sinclair touring Stephen Hawking, who took some major efforts in order to get him underground. No shower underground, instead vacuum above ground and a special rail car to get him there. The radioactivity in the water and heavy water was purified to about 1 billion times better than tap water. So putting all that together, these are the results. What you see in the vertical axis is the flux of neutrinos as inferred from our measurements. The predictions by this particular one by Ecole and his collaborators in the year 2000, the prediction of the total number of electron neutrinos in the sun was in this band. For the reaction that we observed, the charge current reaction sensitive specifically to electron neutrinos, we observed only 1/3 of that number, similar to what was observed by Davis in his measurements. However, unlike the other experiments that had been done by that time, which were sensitive only to electron neutrinos, we had this other reaction, which was sensitive to all neutrino types. And what we were able to show is that with 5 sigma, 5.3 sigma, or less than a chance in 10 million, that neutrinos from the sun, which started as electron neutrinos, did not change into other neutrino types. By far, the probability was that what we were observing was, in this reaction, 2/3 of them being muon and tau neutrinos, and only 1/3 of them being the number that corresponds to the original type of neutrino produced in the sun. So there was agreement with the solar model calculations, which gives you confidence in the calculations of the sun. And there was a new process, which essentially was clearly showing neutrino flavor change in a different way than what the Super Kamiokande measurements for atmospheric neutrinos had shown a few years before. These were electron neutrinos, and you were not only observing their disappearance, you were also observing their reappearance, which confirmed processes of oscillation, which also involved interaction with the electron density in the sun. So why was it important for these measurements to be made? Well, obviously we pursued them in the first place to do basic science, and we certainly observed physics that goes beyond the standard model. It's also important, of course, that neutrinos and their properties can have a significant influence on cosmology, or on how the universe has evolved since the Big Bang. You can also, by understanding how the sun burns, address one of the main points in the universe where we, or elements that we are composed of, are created. They are produced in elements, in stars like the sun. CNO processes are processes that occur in the sun, or stars like them, or other heavier elements are produced in collapsing stars, supernova. But in addition to that, understanding that the calculations of how the sun burns are very accurate is a confirmation of an independent sort compared to the calculations that are made here on Earth using very often very similar processes to try to decide and design how fusion power sources should be designed. And we've now confirmed, in a sense, that those calculations applied to the sun's core, where it's held in place by gravity, that they work in a situation where here on Earth, what we're doing is attempting to do that held in place by magnetic fields. So it's a broad range of implications for this process. Now, this process of neutrino oscillation is an unusual quantum mechanical process where neutrino flavors, electron, muon, and tau, can be expressed as combinations of three masses rather than being unique in their masses. This shows the present thought as to the composition of electron, muon, and tau neutrinos in terms of those mass 1s, 2, and 3. They're created then with this this composition, let's say, of the eigenstate that represents an electron neutrino. And as they oscillate, what happens is the process of oscillation, for example, for a neutrino in a vacuum, you end up with a sinusoidal form of oscillation that depends on various coupling parameters, on the difference in mass of the neutrinos, in the length over which they have oscillated, and on their energy. And so basically, you produce them in this state. When you make a measurement after they have traveled for some distance, you are measuring, if you have a process that's specific to the electron neutrino, because of oscillation, you may measure a very different composition than this and infer that to some degree they look like an electron neutrino, and to some degree muon or tau neutrinos, which is exactly what we measured. Now, this process of expressing the different flavors in terms of the masses takes a matrix form, originally proposed by Pontecorvo for the process, and Maki Nakagawa and Sakata for this broader formalism. And for oscillations, the elements of this matrix to the left of this final matrix here are the ones that are relevant. And in fact, the parameters for 3 of the matrices have been defined. We don't yet know what the delta parameter here, which is active if there is CP violation. In other words, antimatter asymmetry is occurring for these neutrinos. And we don't know, in the case of this process of double beta decay, what these 2 other phases are. But otherwise, for active neutrinos, for ones that participate in interactions with electrons and quarks, as we know them, we have a fairly complete formalism here, although there's an additional formalism referred to as the MSW effect, which brings into account what happens if you encounter a very intense or dense electron density as you have in the sun. And it has an influence on these solar neutrinos. And if you do an analysis not only of our results, but also of other measurements that have been made by Davis originally and by Super Kamiokande and by several experiments that measured the fluxes of the PP neutrinos predominantly, this shows the composition of the different reactions powering the sun that are sensitive, for which there is sensitivity in the experiments. And you do the analysis, you find that this interaction of these neutrinos with the dense electrons in the sun have a big effect on this oscillation, such that the neutrinos exiting the sun, the electron neutrinos originally exiting the sun, end up in an almost pure mass 2 state and effectively remain in that state until they reach our detector. That confirmation tells you what the value of the difference in mass between 1 and 2 is, and it also tells you this dominant mixing parameter between mass 1 and mass 2. Of course, I mentioned already the Super Kamiokande experiment, beautiful measurement of atmospheric neutrinos that for which I was honored to share the Nobel Prize with Takaaki Kajita. And of course, both of us are very conscious of the fact that we represent a very large number of people who, in our collaborations, who did the work to get these results. So here's a summary of the various things that have been measured subsequent to the original Super Kamiokande and SNO measurements. There have been now measurements with reactor neutrinos, one of them being CamLand, for which results were reported shortly after the SNO results, where they looked at an oscillation pattern for neutrinos from essentially all the reactors in Japan that were operational then. The parameters for these 1-2 parameters I referred to are shown here for vacuum oscillation. These are electron antineutrinos that are oscillating, and they fit very well with what one observes for SNO if one applies this Mikheyev-Smirnov-Wolfenstein effect. Other oscillation experiments have taken place and observed oscillations at accelerators. And a comment that can be made about such oscillations in vacuum is that if one observes this pattern, then it implies that neutrinos have the ability to sense the elapsed time in their rest frame, and therefore change type in this oscillatory process as time evolves. If they can do that, then Einstein's theory of relativity requires that they're not traveling at the speed of light, during which the sensing of time would not be possible. Therefore, they must be traveling at less than the speed of light and thus have a small finite rest mass. This is an argument that I've first learned from Hitoshi Murayama. But it's a nice explanation of why observing oscillations implies a finite mass. So this is pre-COVID data, but I think it's pretty close to the present up-to-date information. We still don't know whether mass 3 is greater than or less than the other two masses. So we don't know the so-called hierarchy. And there can be two, normal or inverted. And we do know the various parameters, the ones referred to as between mass 2 and 3 are studied by Super Kamiokande and by other accelerator oscillation experiments. The numbers associated with the 1-2 parameters were studied by a number of experiments studying solar neutrinos and by Kamland. The numbers for between 1 and 3 were studied by the Reno and Diabé experiment, and there are now future objectives of observing other properties of neutrinos, such as their finite mass, or basically the mass scale on which these differences, which we know from oscillation, exist. The CP parameter that I mentioned, which are being studied in very long baseline experiments at Fermilab and in Japan. This hierarchy, we don't know. We don't know whether 2-3 is maximal or not. And we don't know whether there are other neutrinos that are sterile, do not interact effectively in the way that the other active neutrino types act. And there are a number of experiments on that as well. So that gives you a summary up to date on where we are in neutrino physics since the days of the SNOW project. I, in my own research, have moved on to other things, and those things relate to the way in which the universe has evolved, as well as being related to the basic physics of first neutrinos, which can tell us how it is that we think the original Big Bang resulted in producing equivalent amounts of matter and antimatter. As you can see, in this process, energy is converted into matter and antimatter in roughly equal amounts. Somehow the antimatter has decayed away, and we have a matter-dominated universe. Then as the universe expands, the things cool off, and you have the formation of nuclei, as you see at this point, after about 3 minutes. After about 300,000 years, the formation of atoms, and also the formation of the light that we can observe as a so-called cosmic microwave background, from which we've learned a lot. And then eventually you start to have formation of stars, galaxies, and the universe as we know it today. The absolute neutrino mass is an object that is of considerable interest. It influences this evolution, and there are limits that are being applied to it through the models of how the universe has evolved, but it also can be inferred from double beta decay. And then finally, there is this dark matter that has a substantial role in how the universe has evolved, and which is a topic of major study in underground laboratories. In terms of neutrinoless double beta decay, the SNOW experiment has been repurposed or reloaded, if you like, with liquid scintillator, which is now installed. And tellurium is about to be added to that liquid scintillator in a organometallic compound that is also transparent. And about 1,300 kilograms of tellurium in the first loading will enable us to address the question of whether neutrinos are their own antiparticle, or in other words, are Majorana particles, by looking for a peak you observe in the energy of the two electrons that are emitted if the neutrino is its own antiparticle and can be thought of as being emitted as a neutrino and reabsorbed as an antineutrino, leaving you with energetically a situation where the sum of the energy of the neutrinos that are emitted is essentially the differences in the mass between the nuclei that are involved in this double beta process. Right now, on this plot of effective neutrino mass versus the mass of the lightest of the neutrinos, which we don't know in absolute terms in electron volts, you have a situation where this effective neutrino mass that comes into the lifetime for neutrinos double beta decay in this way, involving matrix elements for the particular nucleus and a form factor for the emission. This effective neutrino mass is a property of all of the previous parameters that I mentioned have been determined in these other experiments, plus a couple of additional phases. And therefore, depending upon whether you're dealing with one or the other of these two hierarchies, you can have this relationship between what is measured and the latest neutrino mass. Cosmology is making a significant contribution. The present limits from experiment are this light green patch here. And with the SNO Plus experiment, we expect to be able to push the limits down into this region. It means lifetimes in excess of 10 to the 26 years. In order for this process to take place, neutrinos have to be their own antiparticle, and they have to have a finite mass. And that's the objective in these experiments. And you can see here that the red signal is what you would see if, in fact, you were at this level, the bottom level of existing experiments, what you would see in 5 years of running in the Sudbury, in the SNO Plus experiment. So the situation is that we have this tellurium ready to be installed at the end of this year. We will improve the sensitivity, and we could go at 10 times greater in concentration for a future experiment with greater sensitivity. Dark matter. We think, based on what is observed from a variety of different sources, that it makes up about 26% of our universe. Dark energy is inferred from measurements observing the acceleration of the universe. Us, the matter that forms us, is thought to be on the order of only about 4% of the total, or 15% of the total ordinary matter, total matter, let's say, in the universe. And neutrinos are no longer thought to be a possibility as dark matter particles. And so many different approaches are being taken to search for them. At CERN, they're trying to produce dark matter particles for the first time since the Big Bang. We're looking for particles that have been left over from the Big Bang and that have an influence in the shape of our galaxy. If you measure the velocity of particles, of stars in galaxies similar to ours, what you observe is something like this. Whereas if you simply calculate what the pattern should be based on glowing matter, it looks like this. And there are many other ways in which we infer that dark matter exists. One of the candidates for dark matter, one motivated in fact by supersymmetry theories, and still strongly motivated by that, is a weakly interacting massive particle, or a WIMP. They can potentially interact with ordinary matter and produce a nuclear recoil, but we don't know what the strength of that interaction is. We also don't know what their mass potentially is. And so many experiments in many underground laboratories are approaching this problem. These underground laboratories are at various depths and various volumes for the hosting of experiments. You can see that the experiment area in Sudbury, which we call SNO Lab, is one of the two deepest, along with Jinping in China. The Medan laboratory, referred to as Fréjus here, is shown in this point, and there's also another Stanford laboratory in the US that isn't shown on this plot, which actually comes from measurements made in China. And what you see for the red line are laboratories that are under a flat overburden as opposed to ones that are under a mountain. SNO Lab has many different experiments. It's an expansion beyond the original region for the snow experiment. It has many experiments for dark matter, and I'll just talk a little bit about one of the ones I'm involved in. Ultra clean location everywhere in order to make it easy to maintain cleanliness in your experiment and not have radioactivity get into your experimental area. An example is the Deep 3600 experiment, which has 3 tons of liquid argon looked at by 255 photomultiplier tubes, much in the way that the SNO experiment looked in at signals from neutrinos. This experiment takes advantage of the properties of argon, which are that nuclear recoil, such as would be produced by weakly interacting massive particles, produce light predominantly in a very short period of time, typically the first 1500 nanoseconds or 150 nanoseconds, whereas other radioactivity distributes the light output over as much as 10 microseconds. And that gives you the ability to discriminate against this form of radioactivity by factors of up to 10 to the 9th. In fact, the first data that we have published for 230 days of a little less than a kilogram of fiducial mass in the middle of the detector showed 0 events and enabled us to expand the sensitivity with liquid argon, as you see here, by a substantial amount. Xenon-based experiments don't have quite the same ability to discriminate based on the time profile of the pulse shape of the events, but they have other means of excluding background. They are somewhat more advanced, and there are in fact several additional experiments, LZ and Xenon N-ton, that are about to start operation this year. However, this is a push towards the ultimate sensitivity in this area. And the people working on argon experiments have come together in what has come to be known as the Global Argon Dark Matter Collaboration, a very large collaboration across many countries. Starting with the DEEP experiment, we're now pursuing a much larger experiment at Gran Sasso, and ultimately would go back to SNO Lab with an even bigger experiment. We have support from international laboratories in Gran Sasso, SNO Lab, and the Cannes-Franck laboratory at the border between France and Spain, where measurements will be made of the radioactivity of argon used in these experiments. This is what's beginning to be built in the Gran Sasso laboratory. It takes advantage of the Protodune cryostat, which was developed at CERN. It will copy that cryostat as an outer cryostat for the experiment, and in the inner region, there will be a time projection chamber, which enables you, in addition to doing the pulse shape discrimination I mentioned on the pure light, to drift electrons and determine the location of an event, both through the vertical drift distance and its location in its position, in a much more sophisticated time projection chamber, much bigger, housing about 50 tons of liquid argon, and using silicon photomultipliers, which operate at the 87 Kelvin of liquid argon. These silicon photomultipliers are a real advance in the detection of light and have a very good signal-to-noise ratio. These are 1, 2, 3, 4 single electrons being produced in these detectors. Excellent time resolution as well. To reduce the radioactivity that occurs naturally in argon due to cosmic rays, we have developed a process of extracting argon from an underground location in Colorado. It has been demonstrated to have 1,400 times reduction in the argon-39 content compared to atmospheric argon. And it is being, there is a plant that is essentially all constructed now and ready to be sited in Colorado. which was built by our Italian colleagues. And we will be able to extract up to 90 tons a year from this location in Colorado, send it to a distillation column for which all the parts exist, and the first part has been tested successfully in Sardinia. And everybody uses the Eiffel Tower as a measure of height. You can see they're roughly the same. And then sent to the detector at Gran Sasso. Urania is the term for this site, and Aria is the term for the site in Sardinia. At the Canfranc laboratory, we will test this argon-39 suppression by putting a small container in the existing ARDM detector. So the objective is to move from the present level of deep down to this level with dark side 20K, and ultimately down to a point where, ironically, neutrinos are the background rather than the objective. We expect to be able to have excellent sensitivity all the way down to that point. And in particular, looking at what the dark side 20K experiment can do, these are the existing limits in a measure of the interaction strength versus the mass of the dark matter particle. And you can see that these are the two experiments that are due to start this year, LZ or LZ, depending on where you are relative to the Atlantic Ocean, and xenon n-ton. LZ is in the Sanford laboratory in the United States. Xenon n-ton, this is the dark, in the same laboratory as dark side at Gran Sasso. We expect, with 5 years of counting, to be able to move to this level, and with 10 years to this level, with a very restricted fiducial volume in the central region for dark side, and potentially to push it even further if our radioactivity levels are as low as we expect. So, in conclusion, particle astrophysics has become a major part of the field of particle physics. Underground laboratories are making major progress with experiments that address neutrino properties, such as neutrinoless double beta decay. And there are even underground detectors associated with the long baseline and even the short baseline experiments that are looking for other neutrino properties. And finally, direct detection of dark matter is a major objective of underground laboratories as well. These measurements have significance in particle physics, but also in astrophysics, understanding the sun, for example, and in cosmology, in the sense of understanding all the details of how our universe has evolved. Thank you very much.
Thank you very much, Arthur, for this extraordinary, outstanding explanations, so clear lecture, and extended views of neutrinos in all their kinds. So we have time for questions and comments or points. And please, participants, raise your hands so we can take to question to formulate to Arthur. So I see here Felix Mirabel, please, from I think from Buenos Aires now. So please, Felix, address your questions.
Thank you very much for this. For this wonderful talk. Well, in the map that you showed on underground laboratories, there seems to be no laboratory in the Southern Hemisphere. And as you might know, certainly, there is an idea of constructing an underground laboratory for this type of science, very deep under the Andes, called Andes, the project, because a tunnel will be constructed between Argentina and Chile under a very large amount of rocks. So my question is, in what sense this idea that is not yet a project could contribute to the main issues of, at this time on neutrino physics?
Well, I think that everything I said about neutrinoless double beta decay, and in fact, dark matter detection, the situation is that so far we have seen neither. And the depth that is potentially going to occur for the laboratory in the tunnel there in South America is quite adequate for a number of new experiments with new ideas on how to approach these topics and find new means of detection. Therefore, I think that there's still a substantial role for such a laboratory. And in fact, I haven't heard anything in the last year or so, but prior to that, I certainly was a part of discussions and have certainly written supportive letters for the formation or the creation of such a laboratory. Perhaps you can tell me what the status is. I hope that this is still something that is planned to be a part of this road tunnel that is planned to be built. Is it status in good shape in terms of the potential for it to be built? Because I think it certainly can do good science.
Yes, there are discussions, and the tunnel should be constructed because of economic reasons, the impact that will have in the region in South America. But the present situation since the start of this pandemic has in some way stopped the economic situation is not ready for the construction. But my question was referring to essentially whether there is an importance, some particular importance on these issues to have a laboratory in the Southern Hemisphere. If it could help the construction of this laboratory that will not be very soon, but in the future, because it is located in this particular region of our planet in the Southern Hemisphere.
There have been, for example, some discussions of repeating measurements of the DAMA collaboration, for example, that had showed some indication of dark matter finite events of a seasonal nature that might take place in the Southern Hemisphere in a different sort of configuration. But I believe that there are some recent results that have not seen anything when obtaining statistics that are somewhat similar to the DAMA results. And so that's one example of a situation where you might see effects that are dependent upon which hemisphere you're doing the measurements in. I don't have another specific instance to mention at this time, but I think I'm missing something in not having a quick answer for you, and I'll think further about it, and we can talk again perhaps.
Well, thank you very much, Professor.
Thank you. If there are other questions or points or comments to be addressed. So meanwhile, yes, and Nick Kaiser here in Paris. Please, Nick.
So thank you for a delightful talk, Art. Great to see you again. So cosmologists are embarrassed by having both dark matter and dark energy. And many of them think that the latter, at least, is indicating perhaps that the standard model of gravity is wrong. And we need to modify general relativity. And there's this huge Venn diagram of dozens of different ways people have thought of doing that. And you're telling us about a modification, evidence that the standard model for particle physics has to be, is wrong and has to be extended. And it's interesting, various people have pointed out, you know, the puzzling thing about dark energy is it's becoming important now. And these neutrinos are going non-relativistic roughly now, you know, on a sort of logarithmic scale of the history of the universe. Do you think these are just coincidences, or should that drive our search for things for theories to test?
One of the wonderful things about cosmology, Nick, is that you and I can attend conferences at which these sorts of ideas that are so broad and so different from what are our normal accepted things get considered. And my feeling about our situation is that, first of all, it's absolutely remarkable that that plot I showed regarding the effect of the mass of the neutrino on measurements of neutrinos double beta decay would have on the same plot both cosmological limits obtained from fitting to these absolutely remarkable lambda CDM models with a relatively limited number of parameters that seem to fit a large fraction of what we observe. And of course still leaves these puzzles that you mentioned, dark energy and so on. So how does it fit in? But you know, what is its origin? But I think what's wonderful about this field is that we can get on the same plot. That what's measured in cosmology and precision cosmology now, together with what's measured in particle physics, can come together. I keep asking people who are doing the modeling in cosmology, if we were to be able to measure in our particle physics direct measurements a finite mass that is a given value or even range of values, how valuable would that be to you in removing one of the uncertainties that you have to fit for? And the answer is, it would be very valuable. And so, you know, would remove some of the correlations that we observe in the fits that we do. And so, whereas I'm not in a position, you're in a much better position to speculate on whether the things that are put forward are likely to be solid things one should take more seriously or not. As an experimentalist, I'm happy to be working in a field where the measurements that we make have significance in terms of attempting to push forward our understanding of particle physics, and at the same time can be of value in cosmology in trying to get a more complete understanding. I am not qualified really to comment on the theories that you're saying are being put forward, because I'm not totally familiar with the astronomical measurements, which are so important in terms of understanding all of these things. But I think it's wonderful that these fields are coming together, and this area of so-called particle astrophysics is becoming a significant part of both particle physics and astronomy as we go forward, and cosmology.
Yeah,
I didn't answer your question.
all you can say about the zoo of alternative gravity theories is there is way too much scope for messing around, and yeah.
I understand.
So I like, there are a few cases where people have said, and this could tie into the neutrino mass.
That doing that gets very complex, obviously, in terms of attempting to understand how the physics relates. Relating gravity to the particle physics of the Standard Model is of course the topic for 40 years at least, and I don't think we're any closer today than we were a while ago. Standard Model has a few chinks in it, but then you expect it to have some, because it doesn't purport to be complete. We don't have gravity in there. There are puzzling things about it just from a particle physics point of view. So we expect to have advances as we go forward, and I mean the G-2 measurements, which still are premature. Basically, all that we heard recently was a confirmation of the same measurements that were made at Brookhaven with better statistics. The promise is to have substantially better statistics and improvements in the measurement as we go forward. That doesn't fit with Standard Model calculations, and maybe we can learn something from that. And neutrinos have to be handled differently. The seesaw mechanism gives something that supposedly is, at least could be considered credible as a way of dealing with neutrino mass. And so we see little chinks and we use it to try to test out models. And that's the way it works in both cosmology and in particle physics. But underground laboratories coupled with fantastic satellite measurements of CMB and other things have made the last 20 years a fascinating period of time to work in, and some fun conferences that you and I have attended.
Indeed.
So I didn't say any answer to your question, but I'm giving you my general feeling about the two fields.
Thank you.
Thanks very much for the questions and the answers, and for sharing your view, Arthur, about the questions posed. Now, I don't see more questions, so I always leave myself to ask questions or to address the points, and these are connected with the two previous ones, and with your answers, and a little, and also of course with your talk, with your lecture. First, I should say that neutrinos, as you know better, are important in all branches of particle physics, and also astrophysics and cosmology. And also I would like to mention that for supernova evolution, explosions, and neutrinos are a signal and messengers very, very important, which is already, I mean, it's by its own, it's a whole branch of neutrinos and of astrophysics. And also atmospheric neutrinos, cosmic rays, now the compact galactic nuclei, or I mean, supermassive black holes. I mean, neutrinos are also together with gravitational waves, and others said particles are very important messengers, and the correlations of all that allows to make a lot of cutting-edge progresses in this field, in the direction you were pointed out. Now, about cosmology, as you well mentioned, particle astrophysics, others called astroparticle physics. There are cosmophysics or cosmoparticles. For dark matter and dark energy, which were mentioned. This school, which have 30 years of activity, so was testimony of the growing up and evolution and the construction of the standard model of cosmology, lambda CDM or lambda dark matter, not to call dark matter now as it has been evolving the knowledge and the updating the knowledge on that. So, at the same time, particle physics, of course. I would like to add what Nick Kaiser previously said. They saying that because of neutrino oscillation, neutrino masses, standard model of particle physics is wrong. No, a standard model of particle physics is not wrong at all. Just needed to be extended, and this is the standard model is a very strong milestone and needed to be extended to particle to introduce or to account, to cope with a mass of neutrinos and neutrinos oscillation. But I should say that now that becomes rather said, even if not theoretically completely accomplished. Not neutrinos and neutrino oscillation, neutrino masses is a part of the standard model, which needed to be extended. That is the way in which physics or science evolves. In the same set, or in parallel or similarly, the standard model of cosmology needed to be extended and need to be extended and in some parts modified. And precisely is in dark matter, concerning the dark matter particle, and we don't know still what is dark energy, but the dark energy is there. So it's not, and dark matter, because of the Ballet clusters of galaxies and large scales, also observations of cosmological structures, it's not possible that dark matter, and this is it does goes to Nick also, and it's not possible that dark matter be accounted or explained by modified gravity alone, because that's already we know that. On the other hand, all the fantastic discoveries of gravitational waves on what is going on are placing strongest constraints on what were proposed these alternative theories to general relativity to account. So for really these alternative theories to general relativity, to gravity, to classical general relativity, which is a very extraordinary correct theory in its own domain of validity, which is classical, non-quantum. That, with all that, we cannot, in a strategy of discoveries, we need to take into account and to make all the correlation of these updated observations and to go in the direction that, dark matter is there, is real particles, in despite of the fact that have not been discovered or detected directly, because the energy scale of the mass particles is not at this high giga electron volt mass scale, but is at a lower scale, which is the kilo-electron-volt mass scale. And that will be, for neutrinos, is a great challenge and a really big modern, another big modern set, not challenge, but important branch of research, both experimental, theoretical, to account for this kilo-electron-volt mass of neutrinos, which could be a right-handed sterile neutrino, theoretical, but is also called from the neutrino hierarchy, so of the masses, and is a very, I mean, there are Karlsruhe KIT, Karlsruhe Technical Institute of Technology in Germany. There are the first Katrine instrument, which is going on for the masses of neutrinos, and in project for the kilo-electron-volt and with neutrinoless beta decay and so on. So neutrinos are at the heart of dark matter and cosmology. And for dark energy, it will not be only ordinary neutrinos. It needs some very, very light particle, and because of the energy scale of the observed cosmological constant, say, or vacuum energy at the present universe, which is in the milli-electron-volt. So these are the directions in which we see, I mean, very important, we see the direction of discoveries. And for the Felix Mirabe, for the Felix said point, or the underground detector planet in Andes, or I mean, on the type of for WIMPs, I should say that it is I should say that as you clearly showed in the card of the global mundial running already detectors, I think is not with more advanced technology in the same direction that dark matter direct detection will be discovered. Is really, I mean, all that is good. It was necessary, and is really because of what we have now, very good precision measurement from galaxies, from velocity dispersions of galaxies, of the Milky Way, the more compact galaxies, and so on. What we see, all the problem have with these particles, very heavy, the so-called cold dark matter, which is very good at a large scale, but not at all at the smallest scale, have a lot of problems, and it needed to be addressed. I mean, we're already addressed. There are a lot of clarifications on that. So really, neutrinos have also their room in dark matter, and but not as the ordinary said light neutrinos, but at the kilo-electron-volt as another type, which is, I mean, what Bruno Pontecorvo, by the way, coined sterile neutrinos. So it's this is more or less what I wanted to point out. I mean, and because we were addressing this problem not only for neutrinos, I mean, from the point of view of dark matter, and also now for dark energy, of course. So thank you very much.
Thank you for your perspective.
So if there are more questions, or comments from the audience is the time to address, to address here. And we have not finished still. We are still, we have a nice moment, an important moment when we receive our lectures, and in particular, the Nobel lecture is here. And the school has its own medals. They have its two medals, which is the Daniel Chalonge medal, to whom the school is named, a pioneering French astrophysicist, and one of the founders of the modern astrophysics school in France, and of the Institut Astrophysique de Paris. And the medal, I will put here so it's a surprise award. So I would like to award, even virtually. I hope. The invitation, of course, is addressed after the pandemic, and we will greatly pleased to welcome personally in Paris, and to present and to offer you the medal of the school. So this is,
oh my goodness.
this is the Daniel Chalonge medal.
Thank you.
And
nice.
Which is coined, coined for the school, and coined by Hotel de la Monnaie de Paris, the French Mint.
Oh, beautiful.
Is the French Mint
Beautiful.
who coined it. And in the reverse side of the
Your microphone's gone. We can't hear you.
You can hear.
Now I can.
We can now. I think you were covering up the microphone with your finger or something.
Yes, you hear me?
Not very well.
Do you hear Arthur?
I think it's better if you just hold that back and don't put it up close to the screen. But I see the medal, but hold it back and we can hear you better.
Do you hear now?
Not
Yes,
very
I
well.
see it. Yes.
Perhaps it's your Nick.
That's good. Yes, I do see it.
Also, the upper side of
Now I can't hear you again for some reason.
perhaps is the medal.
No, that's fine. Now I can hear you.
You can hear. So
I
show you first the medal and then explain, because it could be the medal. The medal is, is absorbing the sound waves, of course.
Now I hear you. Good.
And so the upper side of the medal is it shows the mirror of the telescope in which we're observing Chalonge at the south of France, Pic du Midi, by the way, also Observatoire Haute-Provence, very important at the time station, and the French Alps, the French mountains, because he was also was fascinated by climbing, and with his spectrograph mounting, put it in high mountains stations for which at the time, Mietet Blacket and Jungfrau Joch station in Switzerland, 3,500 meters of altitude, where Jungfrau Joch station, Mietet Blacket and others, Le Prince Ringuet, Le Curie, and it was the ancestor of CERN. Before CERN, the discussions were there and evolved there, and Sean Simpsons and many others. And so the lower side is the mountain named after him, because he has a name in France, in the Alps, called Chalonge Peak, the Chalonge Peak, Chalonge Mountain. So this is the Chalonge medal. The first medal was given, I gave to, awarded to Chandrasekhar, who inaugurated the medal. Chandrasekhar inaugurated the school in 94, in 91, and came again in 94. The second awarded of the Chalonge medal was precisely Bruno Pontecorvo, who was very old, and you know the history, I mean, the rich history of Bruno.
I know it very well.
And so in the old times came accompanied by some member of his family. You know, he's Italian from the origin, from the north of Italy, and came to the school. I met them here and was a great supporter of the school. And in 92 was the second Chalonge medal. By the way, he explained me how he arrived, because at the time the solar neutrino problem was at the heart of the discussions, and many proposals and many confusion too, but he was always saying that it's because neutrino oscillation. By the way, he offered me the manuscripts, first manuscripts in which he coined the name esteral neutrinos, and also some of his first ideas on neutrino oscillations, and how described by wave functions, I mean, which is also a real proof of quantum mechanics. You have a wave, not a point. You have the phases and the interferences between the different phases on the different states. So it's very interesting. So, and many others, I mean, many others Nobel Prizes of the school, George Smoot, Sean Matter, Brian Schmidt, and the last here by Zoom, who will come again, Adam Ries. Nick Kaiser also is an awarded of the Chalonge medal. And we have from 2015, silently but always present, Hector-de-Vega, a brilliant theorist, and here in France, an Argentinian as me, and a pivot in the school, and crossed all types of modern theoretical physics and particle physics too, and cosmology. And from 2015, who sadly passed away at the age of 66. And so we have also coined in tribute and the Hector-de-Vega medal also. You are also awarded of the Hector-de-Vega medal.
Thank you.
And is in the reverse side is the Gentleman of Science. It's this has an history. I mean, it's the famous photograph who made the portrait of Hector in one of the schools, because the school has also the photograph, which are the family from Blumenfeld, Erwin Blumenfeld, and France, Germany, France, United States, Princeton, Cambridge, England, and the family also physics and photography, or physics and art. And so it's the Daniel School, the Daniel Chalonge School with thanks, and is science with great intellectual endeavor and a human face. And the recipients of the Daniel Chalonge Medal and of the Ecole-de-Vega Medal have both qualities and are ambassadors of the school. So we are very proud to offer to award you the 2 medals, and I hope this all have an end set, and so this pandemic should also, or transform in some sense, which perhaps will be able to next year to do something more in presence. So in any case, you are awarded of the 2 medals, and we are very proud, and we are very grateful to you to have explained it and to be present today. So this I want. I also meet William Fowler in the school, and his wife, and I mean, I very pleased that you was in some sense collaborator or a student.
I was a student in Kellogg Laboratory at Caltech, where Willie was the director, and he was a wonderful individual. And one of the a characteristic of Willie was the motto he put on his Nobel lecture, which was per astra ad ardua et ludum, which means to the stars with hard work and fun. And that was what it was like to be in the vicinity of Willie Fowler when you were doing science. And that's what everyone should feel about the work that they're doing. And it was always true. I also met Bruno Pontecorvo in 1992 at a conference in Granada. And it was the year before he passed away. He was suffering from Parkinson's rather substantially. But he was very interested in the Sudbury Neutrino Observatory. You know, he spent about 4 years in Chalk River in the late 1940s. And in fact, the paper in which he put forward statements about the possibility of measuring neutrinos from the sun using chlorine was originally a classified Chalk River document that was subsequently published. And so he wanted to talk to me about the Sudbury Neutrino Observatory, which was just starting construction at that time. But he also wanted to learn about friends of his that he worked with. He worked with 2 people at Chalk River and made a measurement of the neutrino mass looking at tritium beta decay in a proportional counter that was the best measurement for about 5 years thereafter at that time. It was 500 kilovolts or something like that, the best that could be done at the time. But Pontecorvo was a fascinating individual, and it was an honor to meet him at that time. So I'm really honored with this presentation, and thank you so much. I hadn't realized this was going to happen today, and it's a great honor to me. So thank you so much.
For us, I mean, for all the school and for participants too. And now you have said that, and I thank you, because it's very important memories what you are sharing.
Very much
I should say that you are also awarded I think in 2005, the Bruno Pontecorvo Prize, which was installed set in Dubna, in the Joint Institute for Nuclear Research. And I traveled to
Dubna to receive that award and was fascinated to realize that Bruno Pontecorvo's son, who spent his years between age 6 and 10 in Deep River, where I lived for a dozen years, was the translator for the ceremony, and so I had great conversations with him as well.
Yes.
And so I have a lot of respect for Bruno Pontecorvo, who was an experimental physicist, who nevertheless made substantial contributions from the theoretical perspective.
Yes. Yes.
Well, as a student of Fermi's, he followed Fermi's model for the combination of experiment and theory in a very effective way.
Yes, he was from the north. I mean, he was educated, and all the family from the north of Italy. I should say is well, the name is very well known, but the name of the city is not Pavia, is not
Pisa.
Parma.
I spoke at his 100th birthday celebration in Pisa, and the university.
Pisa.
The university in Pisa is in the former Pontecorvo foundry, the company business. The university is now founded, is now residing in that location.
We have, I mean, I know many, I mean, I know people and families there who with Pontecorvo mother, very well known of Pontecorvo mother and father there, and the family, as you said, that the family of Pontecorvo, very interesting and cultured persons. And the sons, one of the sons, I think, it was also involved in physics, and has several sons. I met some of them. And also I was in Dubna. I was in the joint, not for Pontecorvo, I mean, was for in Dubna, a very interesting place too. And Bogolyubov was there.
Yes,
so
thank you very much. This has been a wonderful day for me, and I thank you so much for making it possible. And it really has been a pleasure. And I look forward to seeing you in person in Paris in the future. Thank you.
We will keep in touch. Thank you so much. Thank you, and keep good. So
and
thanks.
And the same to everyone. Nick,
thanks
nice to see you. Bye now.
Looking forward to seeing you in the flesh, en présentiel, as we say.
Me too.
Yes.
All the best.
And
bye now.
Properly.
Bye. You are free to leave, Arthur, of course.
Thank you so much.
Okay,
bye now.
So, bye. Thanks to all participants again. And so thanks so much. And we will continue for the next lecture. So now we close the session now. So bye.
Thank you. Goodbye.
Bye. Thank you. Bye. Thank you.